Good morning, students. This is your physics teacher, Sir Glenmark A, and today I will discuss to you kinetic molecular theory and the ideal gas law. The objectives for this topic are the following. At the end of this module, the student should be able to first, enumerate the properties of an ideal gas. Second, solve problems involving ideal gas equations in context such as, but not limited to, the design of metal containers for compressed gases. This will be our topic outline. Topic 1 is about equations of state, and under this topic are the following: the ideal gas equation and the PV diagram. Our second topic is about the molecular properties of matter. The subtopic is about the mole. The third topic is about kinetic molecular model of an ideal gas. And the fourth topic is about the heat capacities. The topic that we are about to discuss can be integrated to your general chemistry subject, specifically on the following learning competencies. Number 1. The use of kinetic molecular model to explain properties of liquids and solids. Number 2. Describe and differentiate the types of intermolecular forces. And for number 3, describe the properties of liquids and explain the effect of intermolecular forces on surface tension, viscosity, vapor pressure, boiling point, and molar heat of vaporization. Now, let us proceed to our first topic about equations of state. In physics and thermodynamics, an equation of state is a relation between state variables. More specifically, an equation of state is a thermodynamic equation describing the state of matter under a given set of physical conditions. It is a constitutive equation which provides a mathematical relationship between two or more state functions associated with matter, such as its temperature, pressure, volume, or internal energy. Equations of state are useful in describing the properties of fluids, mixture of fluids, solids, and even the interior of stars. The ideal gas equation. An ideal gas is one whose physical behavior is accurately described by the ideal gas equation. The PV equals nRT. This is our equation 7.1. The constant R in the equation is called the gas constant. The value and units of R depends on the units used in determining the pressure, volume, the number of moles, and the temperature T. In the table, you have there the values of the constant R. In the first column, you have the units, and in the second column, you have the value. If the units used is liter atmosphere per mole Kelvin, the value of R is equal to 0.08206. If the unit used for the value of R is calorie per mole Kelvin, the value is equal to 1.987. If the unit used for the constant R is joules per mole Kelvin, the value that we have to use is 8.314. If the unit used for the constant R is cubic meter Pascal per mole Kelvin, then the value is equal to 8.314. And if the unit used for the constant R is liter torr per mole Kelvin, then the value that we have to use is 62.36. In the ideal gas equation, The temperature T must always be expressed in terms of the absolute temperature scale, which is the Kelvin. The quantity of gas, denoted by small letter m, is normally expressed in moles. It can also be expressed in terms of the total mass, denoted by m sub total, and the molar mass, or sometimes called as the molecular weight, which is denoted by the big letter m. So m total equals the product of the number of moles n and the molecular weight m. This will be our equation 7.2. The units chosen for pressure and volume are typically atmospheres and liters. However, other units may be chosen. The product PV can have the units of energy. Now let us proceed to our next subtopic, which is the PV diagram. A pressure volume diagram, or PV diagram, or sometimes called as the volume pressure loop, is used to describe a thermal cycle involving the following variables. These are the volume on the x-axis and pressure on the y-axis. This is in fact enough information to fully describe a simple system from a thermodynamic standpoint. The diagrams are useful when one wants to calculate the work done by the system, the integral of the pressure with respect to volume. One can often quickly calculate this using the PV diagram, as it is simply the area enclosed by the cycle. At this point, let us solve some examples relating to our topic on ideal gas equation. Example number 1. A 20-liter tank contains 0.225 kilograms of helium at 18 degrees Celsius. The molar mass of helium is 4 grams per mole. A. How many moles of helium are in the tank? B. What is the pressure in the tank in pascals and in atmospheres? To solve this problem, we have to identify first the given. Our given are the volume, which is equal to 20 liters, the mass of helium inside the tank, equal to 0.225 kilograms, the temperature, which is equal to 18 degrees Celsius, the molar mass, which is equal to 4 grams per mole, or equal to 4 times 10 to the negative 3 kilograms per mole. Letter A. Using equation 7.2 to solve for the number of moles n, we have the number of moles n equals the total mass over the molecular mass, which is equal to 0.225 kilograms divided by 4 times 10 to the negative 3 kilograms per mole. And this will give us 56.3 moles. Letter B. To solve for the pressure inside the tank, we will use equation 7.1. So, from pressure equals nRT over V, we have 56.3 moles times 0.08206 liter atmosphere per mole Kelvin times 18 plus 273.15 Kelvin divided by 20 liters. And this will give us a pressure of 67.26 atmospheres. Now note that in question letter B, we are to express pressure in terms of pascals and in atmospheres. And we already solved the pressure inside the tank in atmospheres, which is equal to 67.26 atmospheres. To convert this pressure into Pascal, we will use the conversion factor 1 atmosphere equals 1.013 times 10 to the 5 pascals. Thus, 67.26 atmospheres times 1.013 times 10 to the 5 pascals per 1 atmosphere equals 6.81 times 10 to the 6 pascals. For our second example, let us consider this problem. A room with dimensions 7 meters times 8 meters times 2.50 meters is filled with pure oxygen at 22 degrees Celsius and 1 atmosphere. The molar mass of oxygen is 32 grams per mole. A. How many moles of oxygen are required? B. What is the mass of this oxygen in kilograms? Again, we have to identify the given to solve this problem. Our given are the volume of the room, which is equal to length times width times height, which is equal to 7 times 8 times 2.50, equal to 140 cubic meters, or 140,000 liters. The temperature, which is equal to 22 degrees Celsius, pressure equals 1 atmosphere, and the molar mass of oxygen, which is equal to 32 grams per mole. To solve question A, we will use equation 7.1. We have N equals PV over RT equals 1 atmosphere times 140 liters divided by 0.08206 liter atmosphere per mole Kelvin times 22 plus 273.15 Kelvin. And this will give us the number of moles of oxygen equal to 5,780.34 moles. In letter B, we are to solve for the mass of oxygen inside the room, and we will use equation 7.2. That is, the total mass is equal to the number of moles N times the molar mass. And this is equal to 5,780.34 moles times 32 grams per mole. And this is equal to 184,971.03 grams, or in kilograms, this is equal to 184.97 kilograms of oxygen. Now, let us proceed to our topic number 2, which is molecular properties of matter. All familiar matter is made up of molecules. For any specific chemical compound, all the molecules are identical. The smallest molecules contain one atom each and are of the order 10 to the negative 10 meters in size. The largest contain many atoms and are at least 10,000 times that large. In gases, the molecules move nearly independently. In liquids and solids, they are held together by intermolecular forces that are electrical in nature, arising from interactions of the electrically charged particles that make up the molecules. Gravitational forces between molecules are negligible in comparison with electrical forces. The force between molecules in a gas varies inversely with the distance r between molecules. When the molecules are far apart, the intermolecular forces are very small and usually attractive. The intermolecular force becomes zero at an equilibrium spacing r sub O, corresponding roughly to the spacing between molecules in the liquid and solid states. Molecules are always in motion. Their kinetic energies usually increase with temperature. At very low temperatures, the average kinetic energy of a molecule may be much less than the depth of the potential well. The molecules then condense into the liquid or solid phase, with an average intermolecular spacing of about R sub O. But at higher temperatures, the average kinetic energy becomes larger than the depth of the potential well. Molecules then can escape the intermolecular force and becomes free to move independently, as in the gaseous phase of matter. In solids, the molecules vibrate about more or less fixed points. In a crystalline solid, these points are arranged in a recurring crystal lattice. The vibration of molecules in a solid about their equilibrium positions may be nearly simple harmonic if the potential well is approximately parabolic in shape at distance close to R sub O. But if the potential energy curve rises more gradually for R greater than R sub O than R less than R sub O, the average position shifts to larger R with increasing amplitude. This is the basis of thermal expansion. In a liquid, the intermolecular distances are usually only slightly greater than in the solid phase of the same substance. But the molecules have much greater freedom of movement. Liquids show regularity of structure only in the immediate neighborhood of a few molecules. This is called short-range order, in contrast with the long-range order of a solid crystal. The molecules of a gas are usually widely separated and so have only very small attractive forces. A gas molecule moves in a straight line until it collides with another molecule or with a wall of the container. In molecular terms, an ideal gas is a gas whose molecules exert no attractive forces on each other and therefore has no potential energy. Now, at this point, let us discuss what is mole. 1 mole of any pure chemical element or compound contains a definite number of molecules, the same number for all elements and compounds. The official SI definition is that 1 mole is the amount of substance that contains as many elementary entities as there are in 0.012 kg of carbon-12. The number of molecules in a mole is called Avogadro's number, denoted by N sub A. The current best numerical value of N sub A is 6.0221419947 times 10 to the 23 molecules per mole. The molar mass of a compound is the mass of 1 mole. It is equal to the mass m of a single molecule multiplied by the Avogadro's number. That is, the molar mass is equal to the mass times the Avogadro's number N sub A. When the molecule consists of a single atom, the term atomic mass is often used instead of molar mass or molecular weight. For our example, let us solve this problem. Consider an ideal gas at 27 degrees Celsius and 1 atmosphere pressure. Imagine the molecules to be, on average, uniformly spaced, with each molecule at the center of a small cube. What is the length of an edge of each small cube if adjacent cubes touch but don't overlap? To solve this problem, let us identify the given. We have temperature T is equal to 27 degrees Celsius and pressure, which is equal to 1 atmosphere, or also equal to 1.013 times 10 to the 5 Pascal. The volume per molecule is equal to the volume of the gas divided by the number of molecules, denoted by big N. This is equal to nRT, over P times the number moles n times the Avogadro's number, or is also equal to R times T divided by the pressure times the Avogadro's number n sub A. Further, this is equal to 8.314 joules per mole Kelvin times 27 plus 273.15 Kelvin divided by 1.013 times 10 to the 5 Pascal times 6.023 times 10 to the 23 molecules per mole. This will give us 4.09 times 10 to the negative 26 cubic meters. If this volume was a cube, the length of its side is equal to L, which is equal to the cube root of 4.09 times 10 to the negative 26 cubic meters, which is equal to 3.44 times 10 to the negative 9 meters. Our next topic is kinetic molecular model of an ideal gas. The goal of any molecular theory of matter is to understand the macroscopic properties of matter in terms of its atomic or molecular structure and behavior. The kinetic molecular model represents the gas as a large number of particles bouncing around in a closed container. Here are the assumptions of our model. Number 1. A container with volume V contains very large number n of identical molecules, each with mass m. The molecules behave as point particles. Their size is small in comparison to the average distance between particles and to the dimensions of the container. These molecules are in constant motion. They obey Newton's laws of motion. Each molecule collides occasionally with a wall of the container. These collisions are perfectly elastic. Number 4. The container walls are perfectly rigid and infinitely massive and do not move. In an ideal gas, the translational kinetic energy kTr of the gas as a whole and the average translational kinetic energy per molecule are proportional to the absolute temperature T. That is, kTr equals 3 halves nRT equals 3 halves kT. The root mean square speed of the molecules in an ideal gas is proportional to the square root of T. These expressions involve the Boltzmann constant K equal to R over Na. That is, Vrms equals the square root of 3 kT over m equals the square root of 3 RT over the molar mass m. The average distance traveled between collisions is called the mean free path, denoted by lambda. It is just the molecular speed multiplied by the mean free time. The mean free time is equal to the volume V over 4 pi square root of 2 r squared V times n. So, the mean free path, which is equal to the product of the speed of the molecule times the mean free time, is equal to V divided by 4 pi square root of 2 r squared times n. And this is also equal to kT divided by 4 pi square root of 2 r squared times p. Note that the mean free path does not depend on the speed of the molecule. Now, let us solve an example relating to our topic on kinetic molecular model of an ideal gas. Question letter A. What is the total random translational kinetic energy of 5 liters of hydrogen gas with pressure equal to 1.013 times 10 to the 5 pascals and temperature of 300 Kelvin? Question letter B. If the tank containing the gas is moved with a speed of 30 meters per second, by what percentage is the total kinetic energy of the gas increased? The molar mass of hydrogen gas is 2.016 grams per mole. Again, to solve this problem, let us identify the given. We have the volume of hydrogen gas equals 5 liters, pressure equals 1.013 times 10 to the 5 pascals, temperature of 300 Kelvin, speed equals 30 meters per second, and the molar mass of hydrogen gas equals 2.016 grams per mole. To solve for question letter A, we will use equation 7.4. That is, KTR equals 3 halves nRT, which is also equal to 3 halves PV. And this is equal to 3 halves times 1.013 times 10 to the 5 pascals times 5 times 10 to the negative 3 cubic meters after converting 5 liters to cubic meters. And this will give us the translational kinetic energy of the gas equal to 759.75 joules. For question letter B, the mass of the gas by means of the ideal gas equation is given by the molar mass times the pressure times the volume divided by R times T. So, the ratio of the energies is equal to 1/2 the molar mass times pressure times volume divided by R times T all over 3 halves PV. This is equal to 1/3 times the molar mass times the square of the speed divided by R times T. This is equal to 1/3 times 2.016 times 10 to the negative 3 kilograms per mole times 30 meters per second squared divided by 8.314 joules per mole Kelvin times 300 Kelvin. And this will give us 2.42 times 10 to the negative 4. This is equal to 0.0242%. At this point, we will discuss our last topic, which is the heat capacities. Heat capacity, usually denoted by a capital letter C, often with subscripts, is a measurable physical quantity which characterizes the amount of heat required to change a body's temperature by a given amount. Heat capacities of gases at constant volume. When volume is held constant, the total molecular energy of the point-like molecules consists only of the translational kinetic energy KTR. When the temperature changes by a small amount dt, the corresponding change in kinetic energy is dKTR equals 3 halves nR dt. From the definition of molar heat capacity at constant volume, denoted by C sub V, we also have dQ equals N C sub V dt, where dQ is the heat input needed for a temperature change dt. If KTR represents the total molecular energy, then dQ and dKTR must be equal. Equating the expressions will give us the equation for the molar heat capacity of an ideal monoatomic gas. The molar heat capacity of monoatomic gases is C sub V equals 3 halves R. For diatomic gases, C sub V equals 5 halves R. Heat capacities of solids at constant volume. For ideal monoatomic solids, C sub V equals 3 halves R. For our example on heat capacities, let us consider this problem. Question letter A. How much heat does it take to increase the temperature of 2.50 moles of a diatomic ideal gas by 30 Kelvin near room temperature if the gas is held at constant volume? What is the answer to the question in part A if the gas is monoatomic? Again, to solve this problem, let us identify the given. So we have the number of moles N is equal to 2.50 moles and the temperature T is equal to 30 Kelvin. For question letter A, the heat needed to increase the temperature of the diatomic gas at constant volume is given by equation 7.9, that is, dq equals ncv dt equals 2.50 moles times 5 halves times 8.314 joules per mole Kelvin times 30 Kelvin. And this will give us 1558.88 joules. For question letter B, if the ideal gas is monoatomic, then dq equals ncv times dt is equal to 2.50 moles times 3 halves times 8.314 joules per mole Kelvin times 30 Kelvin, which is equal to 935.33 joules. This ends our discussion on kinetic molecular theory and the ideal gas law. Thank you everyone for listening.